as you were saying beautifully earlier, this switching off, having gravity manifestly a finite range, doesn't mean that it has to be massive. And that is right. If what we're observing now is the switching off of gravity, it will mean that effectively gravity is massive. And that's why led us to a theory of massive gravity. So massive gravity tries to help tackling the cosmological constant problem by switching off the effect of this cosmological constant. It's switching off the effect of this cosmological constant, not a little bit on large scales, that's what it does, but also on long time scale, and that's more where the huge effect comes in.
Claudia de Rham is a Claudia de Rham is a leading researcher in the field of massive gravity theory, proposing that gravitons have non-zero mass. Today we discuss her book, The Beauty of Falling, which explores the intricate connections between gravity, her lived experiences, and utterly groundbreaking research. Chapters are located below. Please like and subscribe, and I hope you enjoy our conversation. Claudia, thank you for coming on the show.
Hey, Carlos. Hi, how you doing?
Yes, great. Thank you very much. So I'd love to set the table here for the general audience, and we'll be discussing your book, The Beauty of Falling, which I have here in a moment. But first, your book talks about your theory of massive gravity. And I'd love it if you could explain this in the simplest, most basic terms for the audience, please.
Oh my goodness, that's a challenge.
I know, yes, it's hard.
That's the hardest question. We start with that. Okay, great. Well, in our understanding of gravity, we may think of how different masses attract each other. So we may think of gravity as how we get attracted to the Earth. That's our typical understanding of gravity. But throughout the centuries, there's been a better understanding of what this phenomenon really is. So according to Newton, it's a force. And then as centuries went on, Einstein came up with a theory of general relativity, which is the theory of gravitation. And it's really remarkable. It explains how we can think of gravity and how we can actually explain all the gravitational phenomena that we know as, in fact, the curvature of space and time combined together as one fabric, as one quantity. And so the theory of massive gravity includes Einstein's theory of general relativity. We try to ask ourselves whether there could be something beyond Einstein's theory of general relativity, beyond this framework, which may be relevant when we're trying to understand how to think of gravitational attraction or gravitational phenomenon on very, very large distance scales, as large as the observable universe today. So the billions of light years is really long. And it's not really long distance scales because even already in Einstein's theory of general relativity, time and space, they combine into one fabric, and it's quite hard to completely separate one from the other. So the theory of massive gravity actually is not massive in the sense that it's huge. It's massive in the sense that the fundamental carrier of the gravitational phenomenon is a particle that has a mass, and that's the sense in which it is massive. But it would behave slightly differently as compared to Einstein's theory of general relativity on very large distances or very long time scales. So throughout the history of the universe, we have mainly experienced Einstein's theory of general relativity, but it could be that now we've been waiting in the universe for long enough that finally we're starting to see small deviations from Einstein's theory of general relativity, and that could potentially be the imprint of an alternative to Einstein's theory. And for instance, massive gravity is one of those things.
Interesting. And then from the book, and it's a wonderful book. I'll link it in the description for folks to buy it if they'd like. And I highly recommend checking it out. We'll dive into the book shortly. You talk about how massive gravity was around as an idea for decades, right? But then it was abandoned because, well, for various reasons. But
Yep.
yeah.
Yeah,
If you'd like to elucidate that,
absolutely.
yeah,
So in fact, already almost a century ago, already since the 20s, and since the development of quantum mechanics. In fact, now this year we're celebrating the 100 years of quantum mechanics, and very quickly after, in 1927, 1929, people at the time already understood how you can think of fundamental forces of nature as being carried by a particle. And so people understood that you can think of electromagnetism, which is the propagation of light, the propagation of an electromagnetic wave, as in fact, being carried by a fundamental particle, a quantum particle, which is the photon. And people understood that Einstein's theory of general relativity could be understood as also the propagation of a fundamental particle, which is the graviton. And people knew at the time, already almost 100 years ago, that in considering this framework, you could also consider some of the particles to be massive. And so a very natural question is whether, for instance, the photon could be massive, and people explore that possibility. And another question to ask ourselves is whether the graviton could be massive. In fact, this comes in with, has an even longer history than that in trying to understand whether the carrier of fundamental forces could be massive particle. Really, that seems like an abstract concept, but the question people have asked themselves for centuries is whether, when you think of a force, it always acts on any time scale, on any length scale, or whether there's a point in which it switches off. And in fact, we know, for instance, that the weak force, do you know about the weak force?
Yes, a little bit. Yeah.
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 But it's not something we're very familiar with in our everyday life. At least I'm not very familiar with in my everyday life. You'd be more familiar with the weak force if you're, for instance, a doctor doing medical imaging with some of the PET scan. People are using the weak force, but otherwise in our everyday life we don't typically think of the weak force as being the same thing as electricity or electromagnetism, because we don't experience the weak force, and we don't experience the weak force because it only operates on very, very small distance scales, on subatomic scales. And so that means that there's a mechanism that switches off that phenomenon, that switches off that force in our everyday life. And it only operates on when you're looking at a subatomic structure. And so it's a very natural question to ask ourselves whether the fundamental forces of nature always operate in the same way as you go to bigger and bigger distances, or if it will be the case that those forces will also switch off at some point. And then my camera decided to zoom on me. just
Well, that's still okay, actually. Yeah, that's still all right. I still have you in frame. That's funny.
Let me go back a little bit. I don't know.
Yeah. That's okay.
So
If you go over to your left just a little bit, that might be a little helpful. Oh, that's perfect. Yeah, okay, that's great. Thank you.
So that sense of whether a force could switch off, I can describe it as having a force which has a finite range as opposed to an infinite range. This is such a natural question that even Newton himself considered that in the 17th century. So when you think of Newton's theory of gravitation, think of the way he phrased it, but he also explored all other alternatives. And he explored the possibility that gravity could have a finite range, a finite reach. And so it would have been the case that if you consider two masses which are quite far away from one another, not only things would get diluted as a distance, but there would be a point where things would just switch off. And that observationally, we don't see that happening on solar system scales. We don't see that happening in the galaxy. But it could be that if we ask ourselves what is happening on very, very large distances, on scales as large as the observable universe, cosmological distances, maybe the weird phenomenon that we are observing, that we are seeing nowadays, maybe this is just because gravity is starting to behave differently on those scales. But already Newton himself considered the possibility that gravity could switch off, and Laplace after him. And then when it came to the point of formulating gravity much more in a field theory sense, in the development of quantum mechanics and quantum field theory, So now 100 years ago, in 1925 and moving to the 1930s, people considered the possibility that gravity could be massive. Again, not in like very big, but in the sense that being of a finite range, or in other words, what that means from a particle physics point of view is that the particle that carries that phenomenon, that force, is a massive particle. Like is the case for the carrier of the weak force. But there was an issue with that. So people tried it out and they realized that they couldn't make sense of such a phenomenon without having lots of pathologies that they couldn't make sense of.
Does massive necessitate a finite range?
So it's a consequence. And I like the way you phrase your question because it goes both ways, in fact. It's absolutely true. It goes both ways. So if one way to think about it is you think of if you have a big mass, if you attach to something very massive, it's going to be harder for you to move along with it. So you can think of the notion of mass at a pragmatic level in some sense, in that it impinges your motion. It stops your dynamics in some sense. So the notion of mass infers that there's a finiteness in how far away you can go in the range of the force. But I like the way you phrase the question because it's the other way around. You can ask yourself, does finite range implies a mass? And the answer is yes. In fact, it is. You can think of however you want to consider a phenomenon which is a finite reach, that in some sense effectively has to be manifested through something which is effectively massive. So there is a correspondence there, indeed.
So yeah, so when we think of light has no mass, right? So photons
That's
have no
right. That's right.
mass.
That's right. That's right.
So do they? So I guess they don't have a finite range, but they do have a certain amount of time it takes to have it at
So
that.
that's a speed. It has a speed. Yeah,
Oh,
there's
okay,
the
yeah,
speed of light,
yeah, yeah.
just like there's the speed of gravity. You can ask yourself the same question, and they have the same speed, light and gravity, or I should say light and light, or light and gravitational waves. They have the same speed in the vacuum. It's 300,000 kilometers per second, roughly. But in terms of range, what we're asking ourselves is something slightly different. Of course, it takes time, and that's a very important concept. It takes time for instance, the electric force between any two charged objects takes time to get communicated between those two objects. Just like it takes time for us to see light from the sun. We only see the sun as it was 8 minutes ago. But we also only feel the gravitational pull from the sun as it was 8 minutes ago. So in fact, if the sun were to switch off completely, we would only see it in 8 minutes. We wouldn't see it straight away. So it's not instantaneous. And so light, like gravity, they have a finite speed in which information is communicated. But what we're asking, rather in the sense of whether light could be finite, is not in terms of its speed, it's in terms of how far it can propagate, or whether there's a point where it switches off. And in fact, there's never a point where it switches off. If you think of the light from the sun, it will keep on propagating through the universe. And of course, it gets diluted. So it starts at the sun. And as you go in larger and larger distances, you have the flux of the light that gets diluted. So at any one point, if you're further and further away, the intensity of light that you get is smaller and smaller. But there's never a point where it just switches off. It keeps on going. There's never any transition. And so what we're asking ourselves is whether there's a transition at some point to a different kind of behavior.
Understood. Yeah. So and correct me if I'm wrong, but let's say traditional models would say that gravity has an effect across the ends of the universe. Some
Correct.
object
Yeah.
at one end, some object
Yes.
at the
Yeah.
other end.
Yeah. Yeah.
Under massive gravity, is that still the case?
Yeah, you're spot on. That's exactly what it would change. And in fact, in a normal model of Einstein's theory of gravity, and the most accepted model, if you take two galaxies, for instance, which would be located on the other side of the observable universe, from one another. So that's a really big distance. So billions of light years from one another. Technically, they still exert a gravitational attraction on each other, but that's really very, very small because they're so far away from one another. But in order to account for their dynamics and in order to account for how they behave in this expanding universe, you need to account for all of the constituents of matter and energy that fills all of space-time in between. And so you need to account for a lot of energy in between. And that's really the crux of the matter. Whereas in massive gravity, for instance, if gravity had a finite reach, you only need to account for a much smaller part of what is present in the universe to explain what is happening. And so that's where the notion of finiteness starts kicking in and starts having an effect.
The let's see. I wanted to ask you. Let's see. You brought up delight. I do want to get to that in a moment, but first, I want to ask you about a sort of broader question in terms of what do you think for the general public? What are the biggest misconceptions that they have when it comes to gravity?
Yeah, so I think the public understands a lot about gravity, which is great because we really do experience gravity on our everyday
Yeah.
life. So actually, I feel quite fortunate to talk about gravity because this is a phenomenon that people do experience and people do challenge. So that's great. Perhaps some of the things that we often emphasize, and it's a little bit of a misconception or not quite the right emphasis, is that there's an issue with we don't know how to quantize gravity. And people often say we don't know what quantum gravity is. And we have something quite specific in mind when we say we don't know what quantum gravity is, which is we don't know what is the ultimate completion of gravity as a quantum phenomenon at very large energy scales, or at in environments where the curvature is very, very, very curved, dense, very strong. But otherwise, we do understand very well how to embed gravity in a quantum framework and to think of gravity as being a quantum phenomenon with quantum fluctuations. And we use that. We, in fact, use that at the very beginning of the universe in trying to understand whether there would be quantum fluctuations of gravity, and those quantum fluctuations of gravity can have an imprint on the sky as we see it. And there are observations out there trying to look for those. So we understand very well a lot of the phenomenon related to gravity and how it works at the interface with all of the other fundamental forces of nature, all of the other constituents of nature, and how, for instance, particles work. What we don't understand is how to make sense of gravity as a quantum phenomenon if you dive within the center of a black hole. So maybe that's another misconception as well, which is you can imagine the black hole at the very center of a galaxy. I think we have very strong observational evidence now that there is a black hole at the very center of a galaxy. And it's not that our understanding of nature, understanding of gravity fails if you were to dive in the black hole. In fact, you can go through the black hole. Probably it won't be a very pleasant experience for you. I don't know. As you do so, someone has to find out and then never come back. So that's a bit of an issue. But we do think we understand very well how to describe what would happen. And we think we do because in fact, the environment there is not very curved, it's not very intense. And the level of curvature there is at the edge of the black hole, and even as you enter the black hole at the center of a galaxy, is in fact not that big. And it's comparable to the level of curvature that we have here in the solar system. And we understand gravity in the solar system so well, really incredibly well. So we think we understand really well what would happen to us if we were to dive inside the black hole. And this is really the issue. The issue is that we understand very well what would happen if you dived inside the black hole, and we understand that you will be inexorably pulled towards the center. And that we understand, and we think is a prediction. And the issue is that you'll be pulled to the very, very center of the black hole. And this is where our understanding of gravity fails. This is where taking gravity as we know it and thinking of it as a quantum phenomenon stop making sense, because in quantum phenomenon, in quantum theory, in quantum mechanics, in quantum field theory, we know that we can't ask ourselves quite the same kind of questions. I can't ask myself, where were you at that time and at what speed were you traveling? We can't ask that question. But what we can ask ourselves instead is, what was the probability for you to have been at that place at that time? We can ask ourselves those kind of questions, and you can answer. We can answer the probability I make an experiment, and I can estimate the probability of a given outcome. And if I make that experiment once, I will get an outcome. I don't know exactly what the outcome will be, but I will get an outcome. And if I make that experiment 1,000,000 times, then I should have a probability of outcome which is consistent with what we had expected with our computation. But if you take Einstein's theory at the very, very center of the black hole, and you ask yourself this kind of question, you ask yourself, what would happen if I make that experiment? What will be the outcome? You interrogate the theory, and the theory tells you, well, you will have more than 100% probability for this outcome to happen. And that, simply doesn't make sense. You know that you should simply stop asking the questions, because the answer makes no sense, and you can't work with that.
Interesting. So what do we do about the extra probability? How do we fix that?
So how do we fix that? Well, that's that's for you to figure.
Oh, great! It's for me. Just kidding.
No, so this is one we need to. That is where we need to have underlying understanding of what our theory of quantum gravity is. This is where we know that there's a lack in our knowledge, and we need to dive deeper into the layers of our knowledge. This is where we know that we need to uncover a more fundamental description of the nature of space-time, of the nature of reality in those kind of environments. What precisely it is, we may or may not have some ideas. Probably string theory is the best game in town at the moment, but there are other alternatives out there. But the reality is we don't really have a fully, completely well-packaged setup, which tells us precisely how to make calculations in there, predictions in there, and then compare them with observables.
Sure. And I want to stay on the topic of black holes for a moment. So there's this irresolvable conflict between general relativity and quantum mechanics. Well, in a few ways, but specifically with black holes. I was wondering, does massive gravity help shine any light on that or resolve any of that conflict?
Yeah, so that's again an excellent question. And at face value, I would say no, I wouldn't expect it, because what happens with massive gravity is really we're asking ourselves the question of whether gravity could behave differently on very, very large distance scales, very large time scales, and that should be a phenomenon that we start observing and seeing when you're looking very, very far away. But if you're looking at this conflict between gravity and quantum mechanics at the very center of black holes for quantum gravity in very curved environment, this is really a conflict that occurs when you're looking at things at very, very small distance scales. And so changing the way you describe gravity at very large distances shouldn't start having an effect on what happens at very short distance scales. One would have expected that we can separate out the different scales, we can separate out the different phenomena. And if you look at, for instance, if you want to ask yourself, how do waves behave on the ocean, you shouldn't really be too confined into trying to understand what is the particle description of what comes into the water molecules that make it the fluid of the ocean. So we like to separate a little bit the way we understand different phenomena at different scales. And so if by analogy there, when you're thinking about massive gravity, you may more think about what happens with the waves on the ocean, whereas when you're thinking about quantum gravity at the very center of black hole, you're more thinking about the fundamental particle description of what comes into the water molecules that makes the fluid, that makes water. And so you'd expect you don't need to be too sensitive of one to be able to describe the other. So the short answer is we shouldn't. No. But in reality, it's never it's never quite that simple. And so it's not like you can just say, I'm going to consider a theory of massive gravity where things are going to behave differently on a long scale. And I don't need to worry about what happens on short scales, because as soon as you're trying to contemplate that possibility, there's a lot of other things that come along, whether you want it or not. And in trying to address some of those, in particular, what comes along is other ways in which gravity behaves, and they start behaving in a quantum mechanical sense quite challengingly, quite differently as compared to Einstein's theory of general relativity, quite quickly. And so it is possible that, in fact, better understanding how to make sense of massive gravity in a quantum model may help us to better understand how to make sense of general relativity and quantum gravity more generically. You can think of some of the features that we start seeing in massive gravity. They start popping in very early on already, and you may think of this as being a bad sign, but in fact, being able to address it in massive gravity in a much simpler setup may help us, may enable us to get a preview of what may happen for quantum gravity as a whole.
Interesting. And I guess the difference between the small scale and the largest scale or longest scales, is it sort of a linear or gradual difference? Like does the or is it dramatic? Does it like flip at some point?
Yes, so for that depends a little bit on the models. It's true that in a lot of models, when that happens, it's quite a sudden flip. So for the
Hmm.
weak force, for instance, it's really a sudden flip. It's an exponential flip. It's an exponential suppression, and a lot of the case, you'd think it should be very gradual and you should never know where you are along the way. But in fact, when you come up with models in practice, a lot of the time is much more um, abrupt than what you may
Mm.
have anticipated. But precisely the scale at which that happens and how smooth or how abrupt it is depends on the exact implementation, on the exact model.
Okay, cool. And is it the same for gravity too? Is it like the
So
weak force? Is it okay?
yeah,
Interesting.
that's right. That's right.
Interesting. It'd be helpful, I guess, for each of the forces, is it, can you go one by one? Like, is it linear or is it sort of dramatic flip for,
Okay, so we can talk about the
yeah.
different forces of nature that we know of so far.
Yeah, yeah, yeah.
So there's gravity, and if you take Einstein's theory of general relativity, you think that it's a massless phenomenon, so there's no transition, no transition at all, and you shouldn't even be confined by the edges of the universe, if you were. It goes all the way up to infinity to some extent, whatever that is. For electromagnetism, the particle there, the particle of light, which we call the photon. At the moment, we also think that it is a massless particle, or at least we have an upper bound on how massive that particle would be if you had a mass. In fact, let me just say as a little tangent, in fact, the constraints we have on the photon, the constraints we have on light, weaker than the constraints we have on gravity, than the constraints we have on the graviton. So we actually understand gravity better than we see light. It's incredible.
Wow.
Yeah, and that to me, sorry, it's a little bit of a tangent, but that to me
That's
is
really cool.
it's really really cool because we have only started communicating through gravity, if you were, in the sense of observing gravitational waves, observing what I like to call light, for the past 15 years, for the past 10 years. Well, before that, there were some other evidences that there were gravitational waves out there, but it's only 10 years ago that there's been the first direct detection of gravitational waves here on Earth. And yet, in these 10 years, we gathered so much information about the behavior of gravity the behavior of gravitational waves and the constraint on the mass of the graviton that is better than all the constraints we had before on the mass of the photon, on the behavior of light itself with that respect. So for that quality, we understand gravity better than we see light to some extent. Okay, so that was just a tangent, but if we go back to the other fundamental forces of nature, there's the weak force. And in fact, the weak force and the electromagnetic force are combined, are unified into an electroweak phenomenon. So we understand that the weak force is weak because the particles that carry it, the W and the Z boson, they're massive particles. And so rather than the force that they mediate being diluted with the distance simply, there comes a point where there's an abrupt force, an abrupt transition. And so we call this a Yukawa suppression. It's really an exponential suppression. And so there comes a point where simply we don't experience that force anymore. And that's why when we're looking at our human scales, everyday scale, we don't experience this weak force at all. And then the final force, fundamental force of nature that we know of is the strong force, which is really responsible for what's happening inside the very nuclei of the, it's responsible for what happens within the neutrons and the protons in the nuclei of the atoms. And there we think that the particles that carry this strong force, which we call the gluons, they are massless particles. But the reason we don't experience the strong force in our everyday life is because there's a different phenomenon that comes in, which is one of confinement. And that in itself only operates on the very short distance scales as well. But that's a slightly different phenomenon.
Interesting. And one thing that you mentioned in the book a little bit, or maybe I heard it in an interview, is I get comments sometimes on videos. I have a few physics related videos, and I've called gravity a force. And I've gotten comments on people saying gravity's not a force.
That's right.
But I think you're team force, right? And I was wondering.
I'm team force, yes.
Yeah. Can you explain that?
Yeah, absolutely. No, it's true. And I think this goes back to one of the point you were making earlier, some of the misconceptions. One of the misconceptions is indeed whether gravity is a force or not. So we may hear that gravity is not a force because we should think of it as the curvature of space-time. Which is absolutely true. I'm not disagreeing with that. But there's still deep down a force in gravity, which is in fact manifested by gravitational waves. And we have detected the force of gravity. When gravitational waves pass through, they distort space along the way. And so in the detection of gravitational waves, what actually has been detected is the passing through of a gravitational waves and the effect it has, the force it had on space-time along the way. And it made some mirrors, which were located in these interferometers, 4 kilometers apart, effectively change distance compared to one another by an amount which is smaller than the size of a proton. So it's a very, very, very small effect, but still the passing of this gravitational wave has had an effect on space between those mirrors and is a force that you can experience and that you can detect. So deep down in gravity, there is a force. I think we typically say that gravity is not a force because if I want to, for instance, explain how I feel the pull of the Earth on me, I can explain that without any force at all. I can explain that just by my motion in a curved space-time. And so I can separate out the notion of force from that. So that's the first picture. But if you dive deeper into that picture, you can see that even if I take myself and I take someone else, imagine there's someone else on top of me, falling into this gravitational field of the Earth, we will start having motions with respect to each other, which is slightly different because as I get closer and closer to the Earth, I'm going to get more and more attracted. Where someone located just above me, the distance between us is going to get stretched. And so some of those things, you can really depict them as a force of gravity nonetheless. It's not a Newtonian force, but it's still a force of gravity. And it is precisely this phenomenon of gravitational waves, for instance, that we can describe as a force and that we can describe as a particle. And that's why we can explain how to think of gravity at the particle level like all the other forces of nature.
I'd love to tease out a little bit the differences between some of these terms. So the difference between gravitational waves, which you call GLITE in the book, and gravitons. Can you tease? I believe it's like the gravitons are to GLITE as particles are to light, or as
Yeah,
photons
yeah,
are to light,
yeah,
or
exactly,
the light
exactly.
waves.
Yeah,
But I think well, I guess even that abstraction is like hard for me to wrap my head
yeah,
around.
yeah, yeah, yeah.
But how do you explain the difference between GLITE and gravitons?
I think, I think you're right that it may be easier to understand the difference between photons and light.
Mm. Hmm.
Photons are constituents of light. And so what light is many, 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 many photons, in the same way as what light is many, 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 many gravitons. So the graviton, the photon, the particles, they are the building blocks. They are the Lego pieces, if you want. And then light or gravitational waves or light, they are the bigger structure, what the whole thing is. And this is really what we typically experience. But we don't experience the effect of a single one of these building blocks. We experience the coherent effect, team working of all of them together. They all are coherent with one another. They decide to do the same thing. And together they sort of amplify the effect of every single one. And that's what we're actually observing. And that's really quite crucial for light or for gravitational wave because it's very unlikely we would ever see the effect of a single one of them. Uh, but we can see the effect of light because that has been measured. So, in fact, maybe the analogy is like talking about a society as opposed to an individual.
Mm-hmm.
The individual is the particle, is the graviton or the photon, and you can describe some of your feature in itself. And what a society is a collection of individuals, but of course, is not completely innocent. And together, people in a society, they work together and they lead to phenomena that can be observed from the outside.
Mm.
So the difference, another way to see the difference is, again, a little bit in the same way as we were thinking about water. And so glide or light, you can think of them as the wave on the ocean. That's what we're observing. So you're in a boat and you feel those waves. That's what really you're observing. I'm not saying that is quite as simple, but that's
Yeah.
an analogy. Whereas the particles, you can think of them as the atoms of water. And so when you are on a boat on the ocean, you're not really feeling the effect of a single atom of water hitting the boat. A single one of them is quite negligible. But
Right.
all of them collectively together make some patterns that you can observe.
Gotcha. One of the things, I guess, one of the typical visuals we see of uh, when educators are trying to explain gravity, sort of like you have a trampoline or something, and
Yeah,
they
yeah,
move the
yeah,
balls around and stuff like
yeah,
that. In
yeah,
that kind of
yeah,
model, or like let's say a grid, you see
yeah,
the
yeah.
two-dimensional grid, and
That's right.
a massive body in the middle and things moving about it. How do we think about that grid, which represents space, and how light and gravitons, how they operate in that? That's something that's like sort of a step I can't quite visualize.
Yeah. So, um, I, some people dislike that picture of grid or trampoline. I think, to my mind, that's the best we can do with our imagination. It's not so bad. It's not perfect. It's not perfect at all, but it's not so bad. Maybe before I explain a little bit what it would mean for gravitational waves um, to propagate on that grid, maybe it's useful to say, though, that if you make the comparison with a trampoline or a fabric, we are thinking of the trampoline as being curved into something else. We have the height of the trampoline, and so there's something outside the trampoline, and we're sort of thinking about how it gets deformed into that other dimension. Whereas for space-time, there's nothing other than what it is. Everything is space-time. So it's not like it's gliding into a different space. It's not like that. Everything is space-time. And it's not just a grid in space. In fact, it's a grid in space-time. But this is really hard for me, and I think it's really hard for most people to actually picture it in our mind. So we do our best, and I think our best is quite good, in fact. Now, I think it's quite easy to think of what would happen if you think of this grid of space and this grid of space-time, and there's a gravitational wave passing through. What it will do is change the meshing of this grid. So you can actually think you have a straight grid to start with, and the gravitational wave passes through, and so you'll have some stretching of the meshing of that grid in some direction, and it does so in the opposite way, in the opposite direction. So there's animations with that going on. But the beauty with gravity and the beauty with gravitational waves is that it really directly affects how different points in space and time are connected together. The whole thing about gravity being described by the curvature of space-time, really you have to think of gravity as being the thread that connects different points in space and time together. And so if you're thinking of a gravitational wave passing through, it sort of tightens the thread between the different points together, or changes that thread between the different points together. And so the different points on your fabric are being pushed or pulled apart. And typically, if it's a wave, they do so with some oscillations. It doesn't need to, but most of the time it does so. Or the ones we observed, at least, yeah.
Interesting. Okay, cool. That helps. Yeah, when I think about let's say like the trampoline or the grid, I wonder like what everything that we know of, the particles and their forces, that's what's making up the fabric, right? I mean, it's not like some other.
Yeah. So, so that's a good question. You're really diving into what is the structure of reality. So you can think of that's quite interesting. In most of our framework, and that's where some people would like to have something quite different. But in fact, in most of our framework, we are thinking of an empty grid. We can think of an empty grid to start with nothing in it, absolutely nothing in it. And then we can start putting things in it and see the effect of that. So we have a notion, in fact, of what it means to be in flat space-time. And it's not necessarily that gravity doesn't exist there, but we take as the ground zero is just flat space-time with nothing in it. It's just a vacuum. And not only is just a vacuum and there's nothing in it, but it's completely as boring as possible. Everything is completely set up and is as flat as you can picture it. So really very much as if I take my board behind me and I just do straight lines, and I do that in all dimensional space and also in time. That's what nothingness is. And now what happens, things becomes exciting when you actually put things in, and you put a single particle in, and already things start becoming interesting. And that whole fixed structure stop being fixed, and it takes a life of its own, and it start adapting for that single particle that you put in there. And it doesn't need to be a massive particle. It can be a massless particle. So you put something like a photon, it has no mass, you put it in, it's not going to stay there. It's going to want to go. It doesn't want to stay put. But it has no mass. It just has energy. It has pressure. It has energy. It has all the concept. It does exist. So it has something, but no mass. And yet that single thing already affects how the fabric of space-time is. So you can think of gravity more as the response to anything living on your space-time.
Interesting. Okay. The I think so.
I don't know
as
if it
close
was
as,
very.
close as I can. So gravity needs other stuff to do work.
So,
Yeah,
so,
it doesn't work by itself.
yeah. So gravity is a response, right?
Mm.
You can think. I like to think of gravity as the what makes connection between any two masses. So we exist, and the Earth exists, and we don't need gravity. Well, we do, but I can imagine myself without thinking of gravity, and I can do the same for the Earth. But now, where gravity kicks in, where the concept of gravity comes in, is how I get connected with the Earth and I get attracted to the Earth by gravitational attraction, and I can't prevent that from happening. And drop an object, it will fall to the Earth by gravity, by gravitation. So you can think of gravity, in fact, as I was mentioning, it's a thread in the sense that it's the connection between 2 points. It's the connection between any two things in the universe. You bring them together through gravity. So without anything, the only thing they would be gravitational waves. They can bubble in and out of existence by themselves, that they would be. But if you don't put anything else other than quantum fluctuations, you wouldn't have anything other.
Gotcha. And you said a moment ago, well, I think you're elaborating into it's like nothingness of a universe. I believe in the book you mentioned that space time, or at least in the model, space time is flat. Oh, it's curved? No, flat. Is space time curved or flat? Actually, that's the question. Because I'm not sure. Because it's not the near thing, but
Yeah. So now
in
I
your
think
model,
it's
it's
got.
curved.
I think in most people that take in gravity as described by the curvature of space-time, at the moment the universe seems the universe is curved, and it's curved in a particular way. It's not curved in, if you think of it in very long distances, it's not curved quite in the same way as we would think of curvature through the mass of a single mass, through the effect of a single mass. It's curved in a different way, but it's curved, and the effect of this curvature is in fact observed through the expansion of the universe. That's one manifestation of curvature. Uh, and so we see that the universe is expanding, which means that it's been stretched. And we don't, in our mind, this stretching is not something that we think of curvature, but we have to separate ourselves a little bit from that more basic notion of curvature. Curvature can mean different things, and the fact that the universe is being stretched is one manifestation of the fact that it is curved, in fact.
Oh, it is curved. Okay, cool.
Yeah.
I thought for the longest time that the universe was
Oh,
flat.
okay. Yeah. Sorry. So I think there's different level of the questions there. I think you're talking about the spatial curvature. Yeah, and that's yeah. So very very good. So the curvature I was talking about is the space-time curvature, and that's why I was talking about the stretching and something that evolves in time. And so as a space-time, the universe is the space-time of the universe is curved. Now, a slightly different question. Related but slightly different is if I'm thinking at any given time, let me just decide on how I'm gonna measure my time, and I make a choice on that, but let me make it. Let me imagine I'm using cosmological time to measure my clock as a clock. At any given time, so let's say right now, is the spatial universe. So when I look in all spatial direction, is it curved or not on big distances? Not in the solar system, not in the galaxy, but on very large distances. And indeed, you're absolutely right that current observations seem to suggest, well, for quite a while, seem to suggest that it's very close to flat. So the universe is very close to spatially flat. In fact, now there may be some elements that may say that maybe it's not quite as flat as one would have expected, maybe some room for that. But to a very good approximation, let's say that it's spatially flat. And that is in itself quite, used to be quite surprising, because we would have thought that there's no reason it should be so smoothly flat. And that's why people had to engineer particular behavior for the beginning of the universe to explain why it appears to be so especially flat today. And for instance, that's why people were thinking of a period of cosmic inflation during the very beginning of the universe, where the universe had been expanding and stretched at an accelerated rate at the beginning of the universe so fast that what we're seeing today, all of our universe today, came out from a tiny, tiny little patch at the beginning of the universe. And so because it's been stretched so much, that would explain why things appear to be so smooth, so homogeneous, so isotropic, and so flat today.
Yeah, fascinating. Thank you for clearing that up. Super helpful. Let's see here. There's a lot of different places we could go. But one thing I wanted to get clarification from you from is actually started from the book that caught my eye on page 104. Yeah. Oh, so yeah. Are you gonna remember when it was on page 104? I can read it back.
Let me
Yeah,
try
yeah.
to get my book.
No, I have it in front of me if you
104.
yeah, cross-reference it. No, yeah. So
104. Okay, it's the first time
you'd re-
someone asked me. You cannot put
oh,
a typo in my book.
no, it's not a typo. It's not a typo. It's actually I didn't. You know what? I'm pretty good about catching typos and things like that in the book. I didn't catch a single one.
Okay, good, good, good.
Yeah,
I can show you a few, but hopefully
you
not too
can.
many.
You
Yeah,
maybe I just
yeah,
didn't catch them.
yeah.
But you wrote that, and I guess I'll just read it. I guess because I have it here too. But it says nowadays most physicists, and particularly theoretical physicists like myself, do not believe that there is an absolute ground level notion of truth that will describe the fabric of reality. So that really surprised me. Yeah. Can you elaborate on that? Why do you think?
Yeah, so I think it's funny because for me that's clear, and then I realize that um, for some people they think that we think there's an ultimate truth, and then that's it, and it will stop there. But we know that the more we know, and the more we realize how little we know, and how much more there is to uncover, how much more there is to discover, and so this has been a pattern that has followed us through all of history. And I think we know that we're trying to understand what happens beyond quantum gravity. And once we have a better description, for instance, of what happens at the very center of a black hole, let me say it's string theory. We could say, okay, we have our answer. It is string theory, and let's stop there. But we're still all working. Why are we still working? Because we're still trying to explore some of the things. There's still a lot of questions that beg for answers. And as we try to address some of the questions, there's more questions that come in. And it's not enough to say, let's take string theory. It's not enough to say, okay, string theory is the answer. We're going to want to understand what goes beyond string theory. What are those strings? Why are they like this? Why are they? Is there this number of dimension? Where did that come from? It's, I feel a little bit like a kid where we say something and they ask why is that? And then you respond, and why is that? And I think we can always play that game. It will always be the case that whatever understanding we have, we're always gonna want to push things further and further. It's a little bit like a fractal design where you're getting better and better and more precise. And the more you do that, the more you realize actually there's an inner structure in it and an inner structure in it. And so that's why I think it's never that we think we're going to have a full understanding of everything around us and then that's it. We can just stop. With all what we do is always dive deeper and deeper and deeper in our layers of physics for a better understanding and pushing the frontiers of knowledge.
But yeah, in the string theory, where does I guess in terms of the theories of everything, um, do you have a favorite or favorites at the top of your
Yes, I'm
list?
actually pretty agnostic myself. I think it's amazing to look for different possibilities. There's there are alternatives that people are exploring. There are different ways to think about things. There's nothing which is really perfect. If I'm being fair or not too unfair about it, maybe. Um, but progress is being made. That is true. Um, I, I think it's still true that string theory is probably the most fully fledged formalism out there as a theory. Um, but it's possible that there may be some other alternatives we haven't quite fully thought about. But what we're realizing nowadays as well is that they are equivalent descriptions. So you can describe reality in a particular way, and then you can come up with a different description, and it's not a completely different entity. In fact, there are ways to relate how you came up with a theory. There's a dual description in another theory. And so we're getting to a structure of reality where we can't even say, is this model or is that model? Because both models can be read into one another, and they may look quite different from the outside. But then, in fact, in terms of how you can make prediction, what it is you can compute, and how this will connect with the structure of reality, you can relate them to one another. And so we're getting more and more to, we're looking at the world and we have a given picture of the world, but then it's not really that we can say, is this particular model or is that particular model? There are element of truth in all of them in some sense, and we have to make peace. We have to make peace with that. If you ask me, because you asked me, I am relatively agnostic on precisely what is the realization of that. And also I think it is challenging to really pin it down to something specific. Maybe we shouldn't do that. In fact, maybe this is not the right way to phrase the question. But one of the work that I'm doing at the moment, some of the work which is on the board, in fact, is trying to make more of a direct connection between what those descriptions of the structure of reality are and how consistent they are with themselves in terms of what that implies for measurements, for observations, for experiments that we can do now or that we can do in the near future, and how it may go in one way or it might go in another way. So for instance, one of the things we know in our everyday life, which we all learn to the point that we stop questioning it, is that we cannot go faster than the speed of light in the vacuum. And this is built into everything of modern physics at the moment. But this is not just innocent. This is something that comes in from consistency, relations, and that has to come in from our ultimate fundamental description of reality, and it has to come down to our description of our everyday life. And in fact, that's just one example. Is the example we can connect the most easily with, but there are other examples in the world as we experience it nowadays is in a particular way, and that's not innocent. It's connected to the consistency of the ultimate description of reality.
So, yeah, thank you for elucidating that. That was great. Yeah, we'll never get to the bottom of it, that seems like. So I had a couple more questions. I do want to get to the book shortly, but just a couple more specific questions, I guess, touch on, and we might get to some specifics later in the book too. But I want to ask you about the cosmological constant problem. And would you mind, one, explaining what that problem is for the audience, and how does massive gravity help, I guess, resolve some of that?
Yeah. So I wouldn't go as far as saying that he resolves it, but it's a way to think about it and how towards tackling it, possibly. So the cosmological constant problem is in fact a very old problem since again, since the beginning of quantum mechanics. So quantum mechanics is now 100 years old. And when it came along, general relativity, so gravity, was already a game in town for more than 10 years. So it was a solid thing. It had been proven by the deflection of light and many other things, if you were. One thing with quantum mechanics, and already if you're thinking about particles, let me imagine I'm thinking about an electron. People knew that it's a quantum system, and it can, even if you are in an empty room with nothing in it, you still have some probability to excite electron positron. They can appear and then disappear, so they can virtually be there. So that means that even empty space must be filled with some kind of energy related with, for instance, the electron, and related, in fact, with all of the particles that we know. And so in order to explain the fact that out of nothingness, out of the vacuum, there is possibility to create particles in and out of existence, out of the blue, it must mean that nothingness, or the vacuum, must still be filled with some energy, the energy of the vacuum, the energy of this quantum vacuum. And one would have expected, if we just take the electron, one would have expected that in order for the electron to be able to be produced for a time scale which is related to its mass, over a distance scale which is related to its mass as well, and carrying an energy which is related to its mass as well, that must mean that the vacuum must carry some quantum energy related to the mass of that particle. And so if you just take the mass of the electron, we know very precisely what the mass of the electron is. No one, well, very few people would say that the electron doesn't exist. I think most people agree on the existence of the electron. Most people agree on the mass of the electron. And if you take that mass of the electron and compute the energy that the quantum vacuum should be holding from that electron, it already gives you a huge amount of quantum vacuum energy. And now that quantum vacuum energy, you can think of it as being everywhere in the universe, completely constant. Doesn't matter whether you're here or in outer space or near a black hole or in the middle of the galaxy. Well, it doesn't matter at all. So it's completely constant throughout the universe, and it's been completely constant since the history of the universe. Throughout the ages of the universe, this quantum vacuum of the electron has been completely constant. So it's a constant which is constant cosmologically. Let's just call it a cosmological constant. And in fact, the effect of this quantum vacuum energy is indistinguishable as compared to the cosmological constant that Einstein himself introduced. So now that we have this vacuum that we think should be carrying quantum energy, quantum vacuum energy, and we know that it behaves like a cosmological constant that Einstein introduced, it should have a gravitational effect. And we can ask ourselves the question of how big an effect it has. If you have this energy from the quantum vacuum of the electron, this should lead to an effect on the universe. And we can compute that effect based on the amount of energy there, based on the mass of the electron. Now, the cosmological constant problem is the realization that just in taking very elementary particles like the electrons, non-controversial particles like the electron, already the contribution of those particles to the cosmological constant is way too large. Already, just from the electron, it would lead to a stretching, in fact, an accelerated stretching of space in the universe, which would be way too fast. And it has been known as since the 1930s from Pauli already realized that, and in fact, people before him already, even before his time, that the effect of the quantum vacuum energy of the electron on space-time will make space-time stretch so fast that the space between us and the moon would be stretching to the point that the moon would seem to be moving away from us at a speed faster than the speed of light, which is not, simply insane. And this is just from the electron. Since then, it's been discovered that there's more massive particles out there that should lead to an even bigger effect to this cosmological constant. And if you even think that there could be particles out there with even more and more massive, or even more and more masses, maybe dark matter and even things which are even more massive than dark matter, then we are led with a cosmological constant problem, which is a tension between the amount of energy that we would have expected there to be in the quantum vacuum and the effect this should have had on the accelerated expansion of the universe, which is 120 orders of magnitude too fast. That's 120 orders of magnitude. So that's one and 120 zeros behind it. This is huge. This is huge. 100 in orders of magnitude too fast, this is completely insane. That would mean that there would be not such a thing as a universe as we know it anymore. There would be nothing. Nothing could have been quite the same way. So clearly that's not the case. And so understanding why this cosmological constant or this quantum vacuum energy, which should be a cosmological constant, doesn't lead to such an insane effect on the universe is possibly one of the most puzzling and vexing, I would say. I think one of the most embarrassing problem of modern physics. And it's really, really embarrassing because it's taking gravity and it's taking quantum mechanics, it's taking two of the pillars of modern physics that we think we understand extremely well, based on which all of modern physics is working. And we're taking both of them in a regime that we think we understand very well. I'm not asking the question of what happens at the center of a black hole or at the very beginning of the universe. I'm asking about what happens on everyday scale, on very large distance scales. And so one would have expected things to work out very well. And yet we end up with the biggest discrepancy, not only in science, in the biggest discrepancy in all of the history of humanity. And that is really, really, really embarrassing. So that's the cosmological constant problem. And this biggest embarrassment, I think, in our understanding of the structure of reality, because it makes complete no sense.
Interesting. And then how
So,
does massive gravity
okay, so how
help
is massive gravity
reframe
fit?
it? Or
Yeah,
yeah,
so one of the reason, not me, in fact, it was proposed by many different physicists well before me and before my colleagues. Um, Actually, probably Gregory Gabadazzi was one of the precursors of this, was to try to understand whether we could tackle this cosmological constant problem by switching off the effect of gravity at some point. So we led with this huge discrepancy between the effect of this quantum vacuum energy and the effect on the evolution of the universe, because we take it at face value according to Einstein's theory of general relativity. So remember, we can think of gravity as almost a dictionary. What makes the link between stuff being present in the universe and the effect on space-time? You can think of it a little bit like that. And so perhaps this huge discrepancy is simply coming because we take in the dictionary in a regime where this is not quite the right translation anymore. We need to adapt for the way one thing affects the other. And so if we want to adapt for how a cosmological constant or quantum vacuum energy affects the evolution of the universe, affects the structure and the stretching of the universe, we need to come up with a theory of gravity that behaves exactly as in Einstein's theory of relativity in our everyday life, but at some point switches off. And that's what massive gravity is doing, in the sense that it switches off the effect of gravity, makes it very, very weak, so that we don't need to account for all of this vacuum energy filling all of the fullness of the universe. And it's not just the universe today, it's the effect of this vacuum energy since the very beginning of the universe. This is a space-time model. So the effect, what was present at the very beginning of the universe, that we also have to account in. So it's a huge amount, a four-dimensional huge amount of energy that has an effect on the universe. But if you're thinking that maybe gravity is sort of switching off now, if you had this constant contribution throughout the ages of the universe, there comes a point where its effect can switch off. And so, as you were saying beautifully earlier, this switching off, having gravity manifestly a finite range, doesn't mean that it has to be massive. And that is right. If what we're observing now is the switching off of gravity, it will mean that effectively gravity is massive. And that's why led us to a theory of massive gravity. So massive gravity tries to help tackling the cosmological constant problem by switching off the effect of this cosmological constant. It's switching off the effect of this cosmological constant, not a little bit on large scales, that's what it does, but also on long time scale, and that's more where the huge effect comes in.
interesting. So it does resolve it, sort of, or
So
close.
So I can't tell you. I think it's difficult to tell you for many reasons. The first thing is, for me to answer that question, first of all, I need to have a framework in which I can work with. I need to tell you what what is the context, what is the theory we're working with. And so this was the first step. The first step was to come up with a theory of massive gravity. So we have a framework, we have a blackboard in which we can start working. That already took many years, and people have started thinking about theories of massive gravity since the 1930s. So for 80 years, people have been thinking about it, and already seemed impossible to think about that blackboard to start with. So now we have a theory of massive gravity. We can start working. This is step 0. But the things are complicated. Things are complicated with massive gravity. Understanding, now that we have a framework, we can start asking ourselves, how does a cosmological constant manifest itself on theory where gravity is massive? And what we know is that it is not the same as what it is in GR. And that is, to my mind, this is the good news. But for most of my colleagues, it's a bad news, because it means that all of the framework, all of the ways to deal with it, all of the numerical simulations, all of the dictionary that they have no longer work. And so we have to, we sort of have to reinvent the wheel for this new instrument. We have to rephrase things in a way which is appropriate for the new theory. So we sort of ask. We got what we asked for, but now we have a bit too much to chew. So it's a lot to re-understand what the whole evolution of the universe would be doing in that new theory. And this is where we are. And in fact, for me, this is where I take a step back and I leave my colleagues take over, because they are the experts in doing that. I'm not the expert in doing that. I have a colleague next door, Toby Wiseman. He's an expert in numerical simulations, for instance, and understanding the role of many different aspects of quantum field theory in a gravitational setup. And so he's exploring some of those aspects, which are really, really challenging. But I think it's really, really exciting, I think, because he's understanding much more the structure of that model. So I still have hope. Again, in my mind, whether this is the solution or not, that's not really the way things go. It's never quite that we come up with a model and then we just wedded to it till the end of our lives and we're not going to consider anything else. We are exploring alternatives. We are exploring what is possible. And what is exciting for me is that we're opening possibilities. We're opening a box and we're trying to understand what is within that box and what we can do with what's in that box. It's always the case that we start with a particular challenge, we start with a particular question, and from that, we develop a whole framework to address it. And it may or may not address it ultimately, but what is certain is that we will learn along the way. And everything we learn along the way, we can then use it in situation where we hadn't anticipated before. And that is always the case.
Yeah. So two of the greatest mysteries in that box, and they make up 95% of the stuff in the universe.
Yeah, exactly.
Dark matter and dark energy.
That's right.
Does massive gravity make any statements about those two?
Yeah, absolutely. So for dark energy, that box contains a traditional box that we look at contains dark energy that with 70% of what's in that box is dark energy. Now, really, when I say that, I give the impression that I know what's in this box. Really, what I should say is that I open the box and I cannot see 70% of the box. That's really what it means. Now, in massive gravity, rather than saying that there's dark energy out there, what we say is that we know what dark energy is. Dark energy is just the quantum energy of the vacuum. So maybe let me rephrase this slightly in a way that hopefully will be a bit clearer. So we know that the expansion is accelerating. We know that today. But in fact, that's not so much of a surprise. As I mentioned before, we would have expected that the universe expansion was accelerated already due to the presence of this vacuum energy or huge cosmological constant from particle physics. So this has been known for almost a century. What the big surprise is not really that the universe is accelerating. The big surprise is that it's not accelerating as much as we would have anticipated. So when people understood that the quantum vacuum should be carrying energy that should have an effect on the universe in leading to its accelerated expansion, people knew that it wasn't consistent with what we were observing. And so at the time, they just said, well, surely we're not understanding something. So let's just set that quantum vacuum energy to zero. Let's just say that the cosmological constant is zero, end of story, because we don't see any accelerated expansion of the universe, and we should have seen a lot of it. So it's zero for a reason that we can't quite understand, but probably there's some symmetry that makes that it's exactly zero, and we're not really appreciating the underlying reasons behind this symmetry, but it has to be exactly zero. Now, that was the big surprise, is why it wasn't huge. Now, if it's not huge, we might as well say it's zero. But another surprise that came later, at the end of the last century, so it was confirmed by different observations in 1998, was that in fact the expansion of the universe is accelerating. So it's not zero exactly, it is accelerating, but by a tiny, tiny, really tiny amount, which is 120 orders of magnitude smaller as compared to what we would otherwise have expected. So that really made the whole community wake up again and said, wait a second. First we said it was huge, and then we said, because clearly it's not huge, then it must be zero. But now you're saying it's not quite zero, it's just tiny, tiny, tiny. And that bothers us because there's no reason it should be so tiny. And in fact, if it's just a tiny amount, then it should actually become larger and larger. We wouldn't expect it to be stable by being just a tiny amount. And what I mean by that is stable under quantum fluctuations, but in the quantum framework. So then a possibility is to say, well, in fact, it is still the case that this quantum vacuum energy is zero. The cosmological constant is exactly zero. And instead, what we are actually observing now is coming from something else, which is of very small value. And let's call that something else dark energy. So when you think of dark energy, it's saying, let me ignore all of the issues that I had in the last century about the quantum vacuum and the cosmological constant problem and all of those things. Let me ignore them because there's two big problems for me to face. And instead, I'm just going to address the last 10 years problem about what I'm just observing. So that's one possibility. But what we're trying to do in massive gravity is go back to the original problem and just from the get-go trying to appreciate what is happening with this quantum vacuum energy, how it manifests itself as a cosmological constant, and how it could explain the accelerated expansion of the universe, but not with such a dramatic effect, with a much smaller effect, because we have to change the behavior of gravity on some scales. And that would mean that you don't need to postulate the presence of an additional kind of dark energy out there, because the accelerated expansion of the universe is already explained by what we know is being present from all the particles that we already know exist.
And I'd love to turn to, might seem like a left field thing, but ghost particles
Yeah.
in the book, because
yes.
you've written
Yeah.
that. Oh yeah, and
Yeah.
in the book you've written, and I think it's probably because you didn't want to fill the book with equations, but
Yeah.
that part of the I guess epiphany that you'd had was around this a square root brick which prevents
Ah.
the ghosts from
Yeah.
appearing. So maybe we could like sort of explain that, provide some details around that.
Yes. Okay. So let me try, let me try to do that. So yeah, if we take the brick analogy or the Lego analogy, so perhaps let me just say what a ghost is to start with.
Sure.
Let me see how far the analogy can go. So people have thought about formulating a theory of massive gravity very early on. It's not something I just woke up in the morning and decided to do it because I thought it was fun. It's a very, very natural thing to do. You have Einstein's theory of general relativity, and that's carried by a massless particle. Really, the next question in the book is, what would it mean if it was carried by a massive particle? And we're exploring possibilities. People have been exploring that possibility. The reason it never gained any traction was because it was always seemed to be linked with a fatal pathology, which we call a ghost. It's not me who came up with that term, it's something quite old. A ghost is a particle which carries negative energy, and so it would destabilize everything that you know of. It would mean that you could decay into that ghost instantaneously. And so all of reality would not exist in some sense. There would be nothing there to rely on. There would be nothing, no ground basis for anything to exist, because everything would decay into this ghost particle. So clearly that's not the case. We're here, we're happy, we exist, we can rely on some elements of reality in some ground structure of realities. There can't be those pathologies being present. If you want a theory of massive gravity, if we want an alternative theory of gravity beyond Einstein's theory of relativity, you need to do it in such a way that you don't have ghosts, you don't have craziness going on in your theories. Those ghosts are just a term to say that it's crazy. It's also related to some level of stability. You want to make it so that you can have the theory and it can stay put for a second, as opposed to completely decay away instantaneously into something else. And so this level of stability means that you need to engineer. Just imagine you building a new, you're an architect and you're building something new. You want to build a new skyscraper. And so you're going to do it under conditions which are stable. You're not going to want to do it on the edge of a cliff, for instance. You're not going to want to do it on a cloud, for instance. You want to think of how you're going to set up your ground level. And then from there, you're going to want to make it with some structure. Now, the structure that we have for gravity is, is something that we have particular bricks to play with, but somehow for massive gravity, when we're trying to set up the structure of that framework, it always seems to fall apart in one direction or another, because the bricks are are not very beautiful in their pattern. So at least what we would have used as a brick to start with is more for the rock, if you want, from general relativity, something which is imperfect. And so when you put those rocks together like that, it looks like the whole thing is always going to fall apart, and we can't do anything with it. And so what we have to do is look at that brick from a different angle and maybe put quite a few of them together. You're not allowed to break them. You're not allowed to do anything with them, but you can combine them together in a particular way, so that this is that square root structure, so that what you end up with is an element which in fact contains an infinite number of rocks, but designed in a very, very particular way, so that you end up with something that looks like a brick, really looks like your traditional brick, and it's stable, and you can put them on top of each other, next to each other, you can slice them, and then the whole structure is stable. Once you know how to construct a brick, one of them, it may be very, very difficult, but once you know how to construct one, then you can copy it, and then you can set up your whole architecture and your whole building, which will be stable. But the challenging thing was to come up with a brick that will enable you to do that. And originally, we thought it would be impossible, because they couldn't see how to fit in all of these little rocks together so that you end up with a building block which made sense.
Interesting. Now, how does, I guess, extending the analogy, okay, the bricks are, let's say, the model itself, I mean, it's not like the bricks are
Oh, you know the bricks are the big.
gravitons
Yeah, they
or the
are.
light.
They
Oh, they
are.
are.
Yeah, they are.
The bricks
Yeah,
themselves are
yeah,
gravitons.
yeah. That's the beauty.
Okay.
They are They are not
Okay.
well. They are uh, deeper structure to the graviton. They have some. They are interacting gravitons. So it's a graviton, but it's also gives you information about how the graviton interacts with its friends. That's what it's all about. But yeah, it's a the brick is, if you want, it's about the individuals in the society plus the social rules. It's all of this together. Yeah, yeah.
Interesting. And how is it that's taking the square root of the brick, I believe? Why did that help?
Let me see. That is so in the typical way to think about it, if you think of Einstein's theory of general relativity, you actually have two copies of it. Maybe the best way to think about it again is, I'm gonna go on what seems a long tangent, and I'm going somewhere there, but stick with me. So if you think of light, if you think of light are electromagnetic waves, and if I think of two electrons, two charged objects that are located, just the two of them, and I have light going through, they will. Oh, sorry. Copy this. Let me do it. Okay. Let me go into a long tangent, and let me try to explain why we need this square root structure. But again, let me start with light because it's easier, and let me build my way through that. So how do we produce light? Do you know what's a radio emitter? What does a radio emitter do? Or what does a normal source of light does? Do you know? How
Does
do
it
I produce
do?
light? How do you shine? We all
Yeah,
shine in one way or another.
yeah, I don't
So
know. It's a good
yeah, so
question.
no,
Yeah, just stop
so,
there.
so let's go back to basic. How do I produce light? One way to produce light is I take a charged particle. Let me take an electron. Let me take a picture of this bulb, and then in the filament of the bulb, it's alternative current. The electrons being accelerating back and forth in one direction. They're just doing this. So you have charged particles that just being moving in one direction, back and forth, accelerated. And in doing so, they naturally shine. They radiate light. So you can produce light, you can produce electromagnetic waves by shaking around some electric charges in one direction. Now you can ask yourself, will that produce gravitational waves as well? Because they are massive things and you're shaking them around like that. Are you going to produce gravitational waves when that happens? And the answer is no. Actually, you need a slightly more complicated setup to produce gravitational waves. For instance, if you take the star and you think of if a star is pulsing like this, that doesn't produce gravitational waves. Instead, what we know has been producing gravitational waves are two black holes merging around each other. And what is important in that motion is that you have not only acceleration in one direction, effectively, you have acceleration in two directions. You have something which is in a plane and is not just back and forth. When you have this orbiting motion, you can separate it into the fact that there's acceleration in two directions. So it goes back and forth like this and back and forth like that. So you need two of those, two copies of those, to produce gravitational waves. So in some sense, you can think of gravity as being the square, because there's two of them. You have two copies. It's the square of what another normal theory of a force, like electromagnetism, would be. So the square is in that. And so when we're talking about gravity in a theory of Einstein's theory of general relativity, we always take the square. And we've always been working with the square as the building block. And that seemed to be always confusing. And so what the reason the square root works out is because you need to separate yourself from these two things and just extract one of them to make the analogy with the other forces that we are more used to, like electromagnetism. And when you have just one copy of them, that's what the square root is, and that's what makes the whole structure look much more beautiful.
Wow. Thank you. That was wonderful. That was really super clear. Now, yeah, that makes it. Yeah, that's great. Thank you.
And that's the
Yeah,
connection between between
yeah,
massive gravity and producing
right,
radio waves.
right. Okay, awesome. Um, let's see. And for the model, what experiments have you conducted or planning to
Yes,
conduct?
so,
Yeah.
so I'm a theorist. You don't want me anywhere near your observations or your experiments. The main experiment I conducted is being able to see you and knowing that we're not flying away from each other faster than the speed of light. That's my certain experiment on which I rely on. But in terms of how could we know what is gravity deep down, whether gravity is following Einstein rules all the way up to very large distances, or maybe there's something like massive gravity? Is there any way to see it? And so already in asking ourselves that question, we know that because the difference between Einstein's theory of gravitation and a theory of massive gravity, for instance, is in how gravity behaves on very long distances, as long as the observable universe today, or timescale as long as the whole history of the universe. Because of that, we know that if we want to look for signs of departure between the two models, we need to look at very big distances, very long time frame. And so what we need to do is use the whole universe as our observatory, if you will. So one way to think about it, and one way to look for potential signatures, is again to look in the imprint of gravitational waves. And what I was mentioning in thinking about massive gravity at the very beginning is in saying that it switches gravity off, or the particle that carries gravity is massive, and so it doesn't want to go, it impinges its dynamics, it changes its motion in a way that it wants to slow it down. So it should slow it down. In fact, in a theory of massive gravity, gravity, or really gravitational waves, shouldn't travel as fast as what we would have otherwise expected, which is the speed of light. Now, they should still travel very, very close to the speed of light. And as you look at phenomena which are shorter and shorter distances, so if I think of producing gravitational waves with two black holes, if they are producing gravitational waves in such a way that they're very close to one another, they merge around each other very fast, the gravitational waves that they will produce will be quite high frequency or quite short wavelengths. And so you're not going to see the effect of the fact that the graviton has a mass or that the gravitational waves are a bit slower then. But if you take black holes, which start their journey much further away from one another, originally, when they start emitting gravitational waves, they can be very far away from one another. And so the gravitational waves, light, that they emit have a much lower frequency or much longer wavelength. If you think of the analogy between this and light, it would mean that the color of the gravitational waves would be more towards the red as opposed to the blue, let's say. So you're looking at gravitational waves which in fact carry smaller frequency or smaller energy. It's a slower process. And so because it's slower, it looks at time scales and distance scales, which are much bigger, where the imprint of these departures is more important. And so this is where to look for. In fact, you would ideally like to look at the production of gravitational waves on scales as large as the observable universe itself. Maybe that can be imprinted at the very beginning of the universe. Maybe that's a possibility. But otherwise, what we're trying to do is try to think of the gravitational waves being produced not with the current mergers of black hole that we're observing with LIGO, CAGRA, Virgo. Those are current observer here on Earth that detect gravitational waves with a 100 hertz frequency, roughly. between 1 and 100 hertz frequency. But in the future, there's going to be some space interferometers that will look at gravitational waves on much bigger distances. There will be much bigger instruments, so they can look at much longer wavelength gravitational waves. And so look at gravitational waves for which the fact that they don't quite travel at the speed of light is more significant, and maybe the imprint on that, on the signal, would be something that we can observe. So in particular, if you think of the merger of two black holes, they start quite far away, and as they merge around, orbit around each other, and they lose energy through the radiation of gravitational waves, and they get closer and closer together, and after millions of years, they end up being, they merge and they collide. And so that means that the gravitational waves that they emit at the beginning, they're very low frequency. And as time goes on, they become higher and higher frequency. And so if you have a very small mass for gravity, the earlier part of the signal, the gravitational waves would travel ever so slightly slower than the speed of light. And as the system comes and gets closer together, the gravitational waves will travel closer and closer to the speed of light. And so now you're thinking of this system emitting gravitational waves, and the first gravitational waves they emit, this travel ever so slightly more slowly than the later gravitational waves that are being emitted. And so that means that the signal that we observe will appear more compact, because the gravitational waves emitted first take ever so slightly longer to come to us. And so they're not as delayed as compared to the ones, they're more delayed as compared to the ones that were emitted earlier. So one of the potential ways to distinguish between those models is to look at the waveform of gravitational waves. So not only gravitational waves at a particular frequency, just one effect, but how they evolve as a function of frequencies. And then from that, we could potentially see the imprint of the different dynamics of gravitational waves, and therefore of the mass of the graviton.
Fascinating. Very cool. Great. So I'd love to talk a little bit about the book too. And we've been, I mean, the topics we've been covering are in the book as well. We were just kind of going back and forth and elucidated so much. Thank you so much.
No,
I
thank
learned
you.
a lot. I'm sure the audience will too. Well, I've learned a lot too. But I've spent some time on the book, which you can barely see here. But what's been the reception to the book?
It's been great. It's been really
Yeah.
fun. All sorts of different connection and engagement. So I think one of the most, that I can share different things. I think for me, what's really exciting is to see that this is something that resonates with people, and to realize that it is a very technical topic. It's really, really technical. You can see the equations on the back. It's not. It's something to go through the details of everything. It does require years and years of techniques, but we can share the excitement about it, and people are excited, and people want to know some of the questions that we ask ourselves. It resonates with anyone throughout the planet. It is something that people really want to understand: how the universe works, how gravity works, how we connect it together, what is beyond space and time. And so it's really exciting to being able to share some of the excitement, but also share the fact that even though the process to go through it is technical, in fact, the concepts themselves is something we can communicate quite easily. It's not technical. It's based on things that we can all understand, and we can all get excited and find some ways to connect with. I think for me that has been very valuable. I think something else that has come up is a lot of people come to me, and for them, they may always have been excited about trying to study physics or trying to address some of those questions, but somehow they were scared by the process, or somehow they thought that being a physicist, it means some things very specific, and they didn't fit the box, and therefore they can't class as a physicist, and it's not for them. And for me, engaging particularly with teenagers or younger people who are not quite sure on where to go and if it's for them or not, I think that is really valuable, because we need to be able to address all of those questions in a very diverse way. And so being able to show that there's not a unique way to be a physicist, and you can be someone that sees some problems in a particular way and address them with a particular background, or someone else. In fact, there's value in all of those approaches, and it's not one versus the other. In fact, there's a big value in bringing all of those things together. That's why I think in the book, and hopefully in our discussions as well, for me, it is important to express the fact that it's not about proving math theory is right or math theory is wrong. That's really not why we do science. That's not why we explore things. Of course, we like to understand how things work, but we learn even when we make mistakes, and we learn by looking at the different possibilities. And so in that sense, we can all explore a lot of this together and make progress together. And that's how we learn. And that's how we're going to push the frontiers of knowledge. That's where we're going to get somewhere all together.
Yeah, absolutely. And
So,
oh
yeah.
yeah.
Yeah, I mean,
Yeah.
I think to me, what has been the best is in writing the book already, it became clear and clear why I became a physicist and how much fun there is in becoming a physicist. And I think it is the case, but I hope it is the case, that how fun it is and how exciting it is has been shared with people. And I see people that, for them, they think being a physicist is something really serious. And actually, it's just fun. Really, we're having fun. Now, that's really what counts. Yeah.
Yeah,
Doesn't
it
mean that we just goof
comes through.
around.
Yeah, sure. You're getting stuff done, but you're also enjoying yourselves.
Yeah,
Yeah.
we know what we. I hope we know what we're doing. I think we know what
Yeah.
we're doing. It requires a lot of perseverance, a lot of being dedicated to it. So maybe that's what gives the impression that it's something very, very serious. But you can't be good at it if you can't challenge yourself, and if you can't tease yourself as well. And there's a lot of fun in that. Yeah.
Yeah, yeah. No, your joy and passion for your work definitely comes through in the book, and of course in your interviews and your presentations. That much is very, very clear. And I'd love to ask. So the book, of course, you talk about massive gravity. You talk about well, physics in general, and then you go into massive gravity. But you interweave your own personal
Yeah.
experiences
Yeah.
and you wanting striving to become an astronaut and all of that, which is very cool. I want to ask you, what's more fun, scuba diving or flying a plane?
Yeah. It's very similar and very different. And it's
Mm,
like physics is very similar and very different. Um, it's hard for me to tell. It's hard for me to say, because when you're in it, that's it. It's just that. There's nothing else. When you go flying, you sometimes you have so many other things in your head, and then you go flying. When you're actually piloting, you just focus on that, and how beautiful it's so beautiful. The surrounding is beautiful. The view surrounding is beautiful, but also you have to be really quite focused. So once someone asked me, "Are you listening to music in your headset when you fly?" You don't do that. You really, really focus, and you really, particularly when you. For me, you do all your calculations on pen and paper. I didn't have a computer or anything. So all of your tracks, you have to adapt for the winds and all of this. So you really focus. It's not like you're goofing around so much. It's fun, but there's absolutely nothing else. All the questions about physics, all of the arguments or not arguments or anything else that was happening in my life to the second when I step in the plane, it just completely evaporates. After, I go in the plane and I feel, oh, I really, really need to go to the restroom, and I don't have time, and I go in the plane, and when I start flying, you don't. I forget. You forget that you had to go to and then you finally land 2 hours later, and then you realize, I really,
you
really
gotta go, yeah.
yeah.
I
So,
bet.
so I guess what I'm trying to say, it's the same thing when you go diving. You just literally dive. You plunge yourself in this cold water. Most of the time, it's a little bit cold, and it's so beautiful. But also, you're so focused, and you breathe in a different way. You. For me, I'm so focused on this incredible environment, in this incredible flora and nature around you, that I forget about everything else. So then, when you come back to reality in your everyday life, I can't even make connection between one thing or another and tell you that one is more beautiful or more elegant or more fun than the other, because it's when you're in it, it's just that. And it's like asking me about comparing between going to an extra dimension and coming back in our universe. I can't tell you because it's disconnected in my mind to some extent. Of course, it's not completely disconnected. You learn a lot in all of those experiments, but um, it's quite surreal in that sense. And there's a little bit of the same when you do research, when you do physics, when you're in the middle of this, it's like almost police inquiry, and you go and detective story, and you go and you look at the puzzles and the hints, and you do the calculation. It's really thrilling, and it's a world in itself. And so when you do that, in fact, there's nothing else. When you're really on the board trying to work things out, or in the middle of the calculation or trying to work things out, there's absolutely nothing else in the world. And that is an experience in its own, which is just as much fun, but also to some extent disconnected from reality. And then you come back to real life and you need to do all of those things as well.
Yeah. Oh, it's lovely. I want to ask you too about one of the later chapters before you had, massive gravity. I'm not gonna say figure it out because it's
Yeah,
still,
yeah,
work in
yeah,
progress. Sort of an early intermediate stages, let's say. Uh, write about how you were at a conference and you got scooped by
yeah,
Gregory
yeah, yeah,
Gabadadze.
yeah, yeah,
And I was
yeah.
just wondering, and that must have been what emotion, what a feeling that must have been at the conference, right? But I was
Yeah,
wondering, how
yeah,
did you
yeah.
end up collaborating with him? Like, how did
Yes,
that happen?
I have to give it to him. This is really thanks to him. And that has happened in other situations where you end up not collaborating at all, and quite the opposite. So I think he's really the most open and generous person in terms of let's get things together. He's really dedicated in understanding as opposed to having his name associated with something or another. And so I think he was just amazing in that sense. So I sent him an email, and in fact, the evening before he was giving the talk, when I just realized, I sent him an email, and we were both invited to a dinner for a ceremony of a prize of someone else. So I ended up in the same dinner table as him, and I was I was a little, I was very very junior at the time, and he was kind of a big shot. So in the end of the evening, I went to him and asked him, I sent you an email. I don't know if you saw it, but maybe we could chat at some point. And he said, oh, yeah, I saw your email. It's so similar what we've done. And straight away, he realized that it was very similar, but also it was a slightly different um, way of approaching it, or even though the results were really exactly the same. And so rather than dismissing it, he said he actually embraced and used it as an opportunity to have a new collaboration. And in fact, even the next day when he gave his talk, he made reference to my work, which was really, really generous of him. He didn't need to do that. And the, the the following day, following his talk, that was a Saturday. We were still at CERN, and it was rather empty because it was a Saturday, but we were staying in the hostel on the CERN campus. And so he said, how about you come and have breakfast at the CERN cafeteria? So, so I did. And so we sat down, just the two of us, in a completely empty CERN cafeteria. And it was actually very nice. We started talking about the next step into that and what you would mean. And there was because we had thought about the same thing, but coming at it from slightly different directions, and both thought about it quite intensely, it was very easy to connect, but also to bring our own piece to the table. And so following the breakfast, he said, well, how about you just come along to NYU and in New York, and we can chat some more. So that's what I did. And it was really good. And I think we worked a lot. It was very intense, but very productive. But I think one of the key things is it was really focused on the physics. It wasn't really focused on what is the result, how are we going to write a paper, or any of that. It was very much what's the upshot? How is it working? Really understanding how it's working. And so often we can think about how things will fit in together, but to really put all the pieces together, you need to sit down and do lots of calculations. And sometimes I do some of them on the computer, sometimes I do some of them on pen and paper, sometimes I need to think about how I'm gonna do that calculation, and I need to go to some textbook and check again and stuff. Um, so often it's easy to have a discussion and say, okay, let's agree that the next step will be that, because we think this is the way it's going, and let's move apart. We're gonna go work towards the next step and then we'll reconvene. But he wasn't like that. He was like, okay, let's try, let's check it out, let's do it out right here, right now, on the spot. Let's go through these thousands of lines of calculations. And then we're making mistakes along the way, and that's okay. We're going through it. And so we really worked for hours and hours and hours. But that was great, because you can waste so much time in convincing yourself that this is the right approach, and then you disconnect, you try your things, and then you go into different kind of tangents. And when you come back, it's never quite the same story, and you kind of lost track of where you were. And one person made progress in one direction, the other one made progress in the other direction, but none of them are really the right thing to do. And so actually just going through everything just right here, right now, on the spot, was really, really useful.
I bet. Yeah. And the book, when you talk about your work sessions with him, it sounded they were intense.
They were intense, but I
You did
liked
a
it.
lot.
Yeah, yeah.
Yeah,
I
yeah.
have to say it was good, and I wish I could do that again, because that's how we bring things forward. So I think he may have read that as me complaining that he overworked me, but that wasn't at all the sense. No, it was great. It was really good.
Yeah, it sounded
Yeah,
invigorating for
yeah,
sure.
yeah, yeah.
I want to ask you too, were there any challenges you faced while writing this book? And if so, how did you overcome those?
So, in all honesty, I never thought that writing would be my thing. And even when I started thinking about the proposal with Jeff, he was great. I told him from the outset, if anyone that knows me would say writing is not is not my thing. It's hard for me to come up with words and put them together in a way that makes sense. And so writing, I thought, would be really the biggest challenge. I have the ideas there and how it connects together, but for me, there's a big step between the ideas and how the concepts I want to communicate, and actually fitting the actual words together in a sentence that makes grammatical sense. That was really hard. So I think what I did was and it was quite liberating what Jeff said, just put down everything. Just put it down and don't worry about how it sounds or anything like that. And I think that was very useful. So that I had everything down, all the thoughts and all the thoughts in how I would connect with one another. And that was much easier to then have a picture of how I wanted to connect the personal aspect of my life with the physics aspect. And I think it is through that I realize I don't think I could have ended up doing anything other than what I'm doing now, because everything seems to be connected with experiences in my life. It seems to fit in together in a way that I never needed to force it. It's not that I wanted to have a physical concept and was stretching my head in thinking, well, what can I say as an analogy in my life that would make it work? It was quite the other way around. It was things about what I have experienced, which to me are directly associated with a physical concept. And so it was very easy to translate that into analogies for physics.
Understood. And so besides scientific literature, are there any, you say, books or authors that have influenced you?
So I mean, I've been loving reading the books by Brian Greene. I think it's probably The Elegant Universe was probably one of the best books I read, and I loved it. And then I love the books by Stephen Hawking. But purposely, when I was getting into writing the book, I stepped away from reading any popular science book because I didn't want to get influenced with their styles. I think it was important for me not to follow any particular pattern. Of course, they do the right thing, and they do the right thing for a reason. But I really wanted to make sure that I wasn't just following too much the way they were formulating things, the way they were introducing some of the concept, and the way they were articulating some of the physical concept. So I purposely really stepped back from reading any any kind of popular science book when I was reading the book. So now I'm enjoying it again. And there's a beautiful book by Tasneem Hussein, who's called Only the Longest Thread. And I absolutely love it. I highly encourage you to read it because it goes through historically, maybe I shouldn't spoil it, but it goes through slightly historically, but through different dialogues into different concepts of physics and how this was articulated in different people's mind, but throughout different ages in history and coming at it through different people's perspective. It's beautifully written and it goes through a lot of the physics, but not only the physics, also how and why people are excited about it and how they were thinking about those kind of questions. So yeah, I highly recommend it.
Oh, cool. Yeah, thank you for sharing. Nice. And I was going to ask you a couple of questions left here. So, if you had a blank check, what experiment would you conduct to test your theory of gravity?
That's an excellent question. So for me, what I would really love to is to being able to see the imprint of quantum fluctuations. What I would like to do is see a graviton, however way you can phrase that. So really understand more precisely the quantum nature of gravity. Now, this is not for massive gravity, but if I had a blank check, that's really where I would go. So there's different ways to try to do that, and it doesn't help to have more and more money or more and more energy to collide particles together to look at interferometers which are bigger and bigger, because it's not entirely clear you'll be able to do that. So maybe you want to go into more energy and collide particles together at the at a high energy rate, but maybe you don't want to do that too close to the Earth either. So if I had a blank check, maybe I'll go on the other side of the universe and ask someone to make a little big bang there, so we can observe what is happening there. But I think I need a little bit more than a blank check. I need also an infinite time scale.
Yeah.
So if you want to be a little bit more realistic, one way to get some insight on the quantum nature of gravity is to look at the imprint of the gravitational quantum fluctuations at the very beginning of the universe in the sky, and more precisely on the cosmic microwave background on the surface of light scattering. And so getting more precise observation of the polarization of light in the cosmic microwave background and being able to separate that from other effects and try to bring that down to primordial gravitational waves requires very, very precise and very broad sky surveys. So I would love to go into those directions if I had a plan.
Awesome. Thank you. And let's see here. Without the risk of getting scooped again, I was wondering if you would mind sharing with us, what are you working on now?
Not sure how to tell you.
You don't have to. I mean, it's okay if it's, yeah.
So perhaps it sounds all the same. For me, it's quite different, but some of the things I'm exploring, which is related to what some of the other things I was mentioning before, is making more of a bridge between the fundamental realization of nature, what is behind everything, even if there's not a limit to it, but what is the structural reality, however you want to phrase that question? What is string theory, if you want to say that, or is it an alternative to string theory? What is quantum gravity, or what is the ultimate completion of gravity and reality, to make a connection between that and concrete things that we can experiment with, observe, or or detect. And so some of the things I'm exploring at the moment is understanding if the consistency of the fundamental underlying nature of reality requires some level of symmetries that are patterns that we see in our everyday life. And so if you think of what we are made out of, the fundamental constituents of matter and the fundamental forces of nature, they are embedded within the realm of the standard model of particle physics. And throughout the past the past century, particles have been predicted and then detected really very consistently throughout decades. And that's because there were patterns based on symmetries. And so if you have something here, it means you have something there. That's what I mean by that, some notion of symmetry. It's a bit more abstract than that, but it's sort of related to this. And some of the symmetries, they are beautiful, they are elegant, but also given. They are there, and we can postulate a particular symmetry, or I can think of a slightly different symmetry. In the same sense as if you think of snowflakes, they have a beautiful pattern, they have a beautiful symmetry to it, but precisely the level of symmetry may depend from one snowflake to another, and depending on how they were created, those snowflakes, the environment in the clouds in which they were created, and the pressure, and all of this will make a particular structure of snowflake or another. And so what I'd like to better understand is if there's some guiding principle in the kind of symmetries that we should anticipate based on the fundamental realization of nature at high energy. So based on where all of this came from. Is it an accident that we just ended up with a situation where we have this symmetry for the matter that we are made out of? Or in fact, this is what we had to end up with because there was no other choice? Or perhaps there were those choices and this is one of those choices. So I'd like to understand a little bit more what are the guiding principles in which symmetries are emerging.
Wow, incredible. I can't wait to see the results of that work. We'll be
Yeah, we'll
keeping an
see.
eye.
Yeah.
We'll keep an eye on it. Very, very cool. And the last question I'll ask, this is something I ask almost every guest that comes
Yeah.
on. It's if you could go back and give your 20-year-old self one piece of advice, what would it be?
Yeah, just go for it. Whatever you want to
Mm.
do, just go for it and follow your journey. I think already I was very, very stubborn, but we do spend a lot of time questioning ourselves and wondering, should I do this? Should I do that? And it's sad because you have so much life ahead of you when you're 20 years old. And in fact, everything you do, that's gonna be what you do, and therefore it's gonna be fine. This is what's gonna make you and your trajectory so unique, and this uniqueness is what's gonna make it so beautiful. So just go for it, but enjoy it really. Do enjoy it. Do not only enjoy the present time, but also enjoy what makes your journey be your journey, and that's important.
Yeah, that's wonderful advice for any age,
Yeah,
including
yeah,
now. So yeah, wow, I
yeah,
really
yeah.
appreciate it. And Claudia, I just
Thank
want
you.
to say thank you so much for your time. This was an amazing discussion. I
Yeah, it
learned
was great.
so
Thank you.
much. I mean,
Thank you.
clarified so many different questions I had, answered everything I wanted to ask you. And I'm sure the audience will love it as well. And just want to plug the book again, please. I'll link in the description for folks to pick up your wonderful book. And thank you.
Thank you, Carlos. That was great. And thanks for the amazing questions. They were all completely spot on. So thank you. Thanks. That was
Wonderful.
great.
Thanks so
Thank you.
much. Have a great one.
Thanks.